This webinar that we are conducting is on behalf of the LC3 project team. It's about sustainability approaches for the cement sector. What we are going to look at is from the climate and the resource point of view. So let me take you through the agenda a little bit. First of all, there will be a keynote address by Professor Scrivner. Then the life cycle assessment, the work that Professor Ravindra Gettu and his team were doing along with cement companies. So we will get to know about what are the results of it and how it is implied in the Indian context with the cement industries. I will be taking over the resource availability of in India and how does it link with the current scenario of fly ash and other raw materials. Professor Manu Santanam from IIT Madras is going to share experiences from the fields. And then we have initiatives that has been taken up by the stalwarts of Indian cement industries like Ultratech Cements and of course JK Lakshmi Cements. They will be sharing their own experiences, not only limiting to LC3, but as an Indian cement industry, what they are doing to achieve sustainability. Let me introduce, of course, everybody knows Professor Scrivner, but for all other participants, attendees who are there, Professor Scrivner is the director at the Laboratory of Construction Materials at EPFL in Switzerland, and she is also she works at the interface between academic research and industrial applications for the cement industry. And her major focus is on lowering the CO2 emissions, which has led to the development on working her with the LC3, and which is a promising kind of a cement which can cut down emissions by around 40%. Professor Scrivner leads the LC3 project team globally and has been instrumental in developing it across. So without much introduction more, may I invite Professor Scrivner to give her keynote address. Over to you, Karen.
Thank you very much, Suman. So let me just share the screen.
And just to all the participants, whatever questions that you have, if you can just put it into the chat box, we will take it up.
Okay, so I hope everybody is seeing my screen okay, and thank you for this opportunity to introduce the LC3 technology, which it really has the potential to make a dramatic reduction in CO2 emissions, and to do this very fast. So just to introduce the subject, if we look at how sales of cement are expected to develop, we really see India is one of the regions in which growth will be strongest in order to reply to the Sustainable Development Goals. And the worldwide share from India will go from something around 10% to more like 20%. So today, if we look at how much CO2 is coming from cement in different countries, we see India is pretty much near the world average of about 8%. But if this increase will continue, and if, on the other hand, India is successful in reducing its CO2 intensity of energy, then this share is likely to increase. Now, we can't do away with using cement in concrete, because concrete is by far and away the most used material, more than all other materials put together. If we look at timber, you know, this really cannot go anywhere. If we wanted to replace just 25% of cementitious with timber, we'd have to plant new forests 1.5 times the size of India, and of course wait 30 years for it to grow. And on a per ton basis, concrete is one of the materials that has the lowest embodied energy and CO2. Now, we're ultimately limited by the composition of the earth. The composition of the earth, just 8 elements make up more than 98%. That's oxygen, silicon, aluminium, iron, calcium, sodium, potassium. And because of this, we really are limited to producing Portland cement, because Portland cement is based on very abundant raw materials and can be produced in the quantities we require. So the most realistic option, after, of course, we have optimized the process, which is largely done in India, is to reduce the clinker factor by replacing the clinker we produce in the cement plant with supplementary cementitious materials. This can be fine limestone, this can be fly ash, which comes from burning coal, this can be slag, which comes from producing iron in blast furnaces, and it can be calcined clay. Now, these two in the middle, fly ash and slag, are the problem because, of course, burning coal is the major source of CO2. And most countries, including India, have committed to phasing out use of coal in the next few decades. Similarly, steel is a very CO2 intensive material, and CO2 will be reduced by more recycling, less reduction of primary iron. And we can see even today that the amounts of slag and fly ash worldwide are very limited compared to the demand for cement. So the materials we have that can take this technology of substitution further are really limestone. Limestone is abundant, but the problem is when we go to additions more than about 10%, it just becomes a diluent. And what is really the thing that can change everything is clays, which can be calcined, which become very reactive material. So this was the idea behind the LC3 technology, and particularly the discovery that when we put calcined clay and limestone together, we can get very high levels of substitution. So here we see strength results from what we call LC350. LC350 contains 50% clinker, and even though you have to put in some energy to calcine the clay, this means 40% less CO2. And you can see here at 7 days, you have higher strength than your reference. And you also have some properties like resistance to chloride ingress, which are very much improved. In this slide, we're comparing calcined clay with fly ash and with limestone, alone as pozzolans and also in combination with limestone. And the key message you can see is that in the long term, all these mixtures come to very similar strength, but the mixtures with calcined clay, which are in the red, are achieving that strength much, much more quickly than either the slag or the fly ash. So the LC3 project is led by EPFL. In India, we have the partners from IIT Madras, IIT Delhi, and Tara, and also we have partners in Cuba. So the first question we tackled, I think you'll hear more today from Suman, is what kind of clay are suitable. We have 3 basic clay types. And what we want is to have at least some of this mineral kaolinite. This kaolinite has what's called a 1-to-1 structure with 1 layer of silica and 1 layer of alumina. And this means when it's heated in the range 800 degrees, both the silica and alumina are available for reaction. And it's very important to stress that we don't need to have very high purity metakaolin. We certainly don't want to have material from agriculture regions. This is not at all suitable, but there are many, many kinds of clays available which can be suitable. We've now tested more than 70 clays from around the world. We see in terms of strength development that this kaolinite content is the key factor. And the red lines on this graph indicate the reference strength of the plain OPC. You can see that by 7 and 28 days, we only need a kaolinite content of about 40%. So ideally, you have 40 to 60%. These kind of materials can be available as wastes from other mining operations. This shows reject clays in India, which are good quality for making cement. And worldwide, we have these clays really nearly everywhere. Everywhere you see this kind of yellowy color, you see including most of India, you will have these kind of suitable clays. For the calcination, you need to calcine in this range 700 to 850. If you go higher, then you tend to get a decrease in reactivity due to some sintering. But you can do this calcination either in the rotary kiln or in flash calcination. Both equipments have their advantages and disadvantages, but we really don't see any major impact on reactivity. So this was the small kiln in India we used for our first trials. This led to the construction of this demonstration house, which is still performing well after 8 years now. And this shows you a greenfield plant for the calcination of clay, which has been constructed in the Ivory Coast. What's particularly interesting about this plant in the Ivory Coast is that there it's possible to control the color of the clay with a quite simple technology coming from the brick industry. You see, this is the red clay, but if you don't want to have red cement, you can quite easily, during the calcination, transform this clay to this normal gray color we associate with cement. So one of the key advantages, I'm just going to show one graph, is the chloride resistance. This shows the chloride penetration into samples. We see the black line here as the reference Portland cement. These red ones are the mixtures with fly ash. The red are with slag, the blue are with fly ash, and here the best of all are with the calcined clay. And I think Manu Sananthamam is going to say more about these performance criteria. So just a short word on how this LC3 technology can contribute to India achieving its goals under the Paris Agreement. Even though fly ash is very abundant, it's unlikely to increase in the short term. And in the long term, it will certainly decrease because India as well has committed to phasing out use of coal. Slag is and will remain very limited, and therefore calcined clays are the only solution we have to increase supply without increasing the clinker factor. And I think someone is going to talk more about this, but the kind of contribution we can imagine to the nationally declared contribution for 2030 is around 10 to 15%, which is really very significant. On a worldwide level, what we see is the current average level of clinker substitution today is only around 20%. And this is due to the limited availability of slag and fly ash. If we remove this limitation, if we increase the supply of SCMs by having calcined clays, we can easily imagine to go to a substitution level of about 40%, which would be equivalent to saving worldwide 400 million tons of CO2 per year. And I think on a horizon of something like 2050, we actually could go much further than this to an average substitution level, maybe up to 55%, which would be equivalent to 800 million tons of CO2. So this single technology is one thing which has the biggest potential to reduce CO2, and it can be done at scale and in the very short term. Financially, we made this detailed report. You can download online. We can see in terms of operation, the price compared to the OPC reference can be much lower, and particularly in a scenario of a grinding plant. So if you install a grinding plant close to a source of clay, this can really reduce your costs. So some of the challenges, which I think the team in India can help you with, are, first of all, to find the right clay, evaluate the financial feasibility, look for calcination equipment, because now all the major suppliers are supplying suitable equipment, how to use it in concrete. There are some issues about workability, but we do now have a good range of super plasticizers to mean you can achieve good concrete. And recently, I think we finally got LC3 into the cement standard in India, but there's still work to be done in terms of the concrete standards and codes. So India is really our flagship in this project. It's the country we've been working with the longest, and we hope now the standard on the cement is finally done. We're going to see the fast uptake here and many successful applications. So just to conclude, I hope I've managed to convince you that this is really the future of cements. You know, we don't really have any viable alternatives. We can produce on the same scale as Portland cement, but we can substitute with SEMs. And in terms of SEMs, calcined clays are really the thing we have that can take the substitution levels to higher amounts. And to get similar properties even to OPC, we can do this with only 50% clinker and clays with only 40% kaolinite. So I think this is a very important technology if we're serious about reducing CO2. So thank you very much for your attention. I hope I stayed in time. And if there's already some questions, I'd be very happy to answer them, because I will have to leave in about 30 minutes, I'm afraid.
Thank you very much, Karen, for that very insightful presentation. It's always a pleasure to hear from you. Very, very convincing. And since you will be, we had planned that we will have a group discussion at a later stage, but since you will be leaving in another 30 minutes, I would open the floor to all the participants. If they have any questions to ask Professor Karen Scrivner. Karen, there is a question from Nikki Jackson. Can a twin shaft PFR kilns be used for calcination of clays?
Well, I'm not sure what a PFR kiln is, but in fact, that one I showed you in the Ivory Coast, this is actually a twin shaft kiln. And these are particularly good because this kind of rotary kiln can deal with clays with very different moisture contents. So, you know, if you have the moisture content of the clay varying according to, you know, the kind of season, how much rain you've had, you can operate the different parts at different rates to adapt the drying to the calcination. So I would say certainly yes, but, you know, for the exact details, you would have to contact somebody from the equipment side who could advise you in more detail.
There was one more question. I think it is not much relevant, but anyway, if you can say this, what is the CO2 emissions from a lime kiln? But
yeah, well, I think this may be a confusion, because when we talk about limestone calcined clay, I think some people think we're using lime. And of course, lime is a very CO2 intensive material because there's a lot of CO2 emissions, but we're not using lime, we're using limestone. That's to say it's not being calcined, it's just raw limestone. And raw limestone, when you're just taking it from the ground, this has really almost zero CO2 emissions, just a little bit of energy for grinding, but it's a very soft material. So really the emissions there are for the limestone we use in the calcined clay cement is near zero.
One more question is very interesting, that you have availability claim availability survey for Pakistan.
Yeah, I think you have done this, Suman. You can give people more details, but also we have some partners. Tariq Jamil at I think it's called, the university is called NED or something like that. He's been working on this technology and advising companies there. And if the person contacts me, I can give you his contact details. He can help you more there. But there are very good clays in Pakistan.
Yeah, we have tested from Tariq Jamil. We have tested some of the clays. They are absolutely brilliant.
Yeah.
Well, the panelists can also talk to you, ask questions. But I have certain other things which I would like to put it here, is that you know that the NDC bill has been passed by the parliament this week. So it has been passed by the cabinet before it is presented to the UNFCCC, and then it has passed by the Lok Sabha also. So now it is a rule, it's a law. So what do you think, that if we have to go carbon neutral, or else if we have to save around 1 billion tons, and that's a dream of, that's a commitment that India has made, to save 1 billion tons of CO2 by 2030 and to go carbon neutral by 2070. How do you see the role of the cement industry here? What should they do?
Well, I think, you know, clearly in terms of the big picture, the most important thing, of course, is on the energy side to install renewable energies, to go to electric cars, everything like that. But the contribution coming from cement is always going to be around 10%. And, you know, you cannot stop building. I mean, you have a huge demand for housing, for sanitation. And to satisfy this demand, you have to use concrete. And therefore, if you're going to use concrete, you have to really find ways to reduce its CO2 footprint. The use of LC3 can be the major contribution here. I think we should remember it's not the only contribution, because we always have to remember that we start with the cement, but the cement is used in concrete and the concrete is using buildings. And if we can save at the cement level, we can also save at the concrete level, and we can also save at the building level. So this is very, very important, that we look at the whole chain of construction and look at possible savings on all these levels. And this, I think, is a very important work now, to bring together, you know, materials engineers with concrete technologists, with building designers, to make sure we are using building materials in the most efficient way possible.
One more, sorry, there is another question here, is that can agricultural waste, ash of agriculture waste ash can be used, I think, used again to replace calcined clay also.
Yeah,
I think
well,
it can be, but it's very low quantity. Well, you are.
Yeah, I mean, there's many problems with agricultural ashes. First of all, the quantities available are not high. Secondly, there's very few ashes that really have much reactivity. I mean, we maybe only have rice husk ash, which has any significant reactivity. And locally, this can be used. But there are a lot of issues about how you burn the ashes, because often the temperatures you are using in the furnaces are too high to give you a good pozzolanic material. And ultimately, for common agricultural waste, it's really not the best idea to burn them. Really, they should be composted and put back on the soil. Otherwise, on the long term, you're impoverishing the soil. So because of the low quantities, because of the many issues in processing, and because of soil depletion, I certainly don't recommend agricultural ashes in any large scale.
Thank you. Thank you. There, we have 6 more minutes left. So if anybody has anything, or else before you end, can I just simply ask a question, that if we have to recommend to the government of India that they should take note of LC3 in a big way, what should be that couple of key words that you would be using to give a message to the government of India, that now you will have to sit, not only be passive, but actively look at low carbon cements or LC3?
I think the two key words are speed and scale. You know, 2030 is 8 years away. It's not even that, because we're more than halfway through 2020, 7 and a bit years away. You know, if you're going to meet these targets, you need technologies that you can implement very fast and at very large scale. Otherwise, you're going nowhere. And this is really where LC3 scores, because we have everything there in terms of the technology is all ready to go. We know we have the raw materials available, and it can be done really at very large scale. So that's, for me, always the two key words: speed and scale.
There is the last question that we can take from Imran Khan. If we can read that, as we are discussing here, method of reducing CO2 globally with respect to cement that requires investment also. But cement plants are also multiplied in underdeveloped countries like Pakistan. To how much extent you think it will help in that case?
Well, yeah, this is a tricky question, because we see that cement demand is increasing in many countries. Where LC3 can contribute is that you can increase your capacity for producing cement for a capital investment of maybe 1/4 compared to building a new clinker line. So that's very important. And if you have a plant with many clinker lines, and perhaps some of these clinker lines are no longer state of the art, they can be easily adapted to producing calcined clay. So LC3 really gives you a technology that can enable you to increase the overall cement production at much lower cost than just producing OPC, and at much lower cost and much lower CO2 impact. Also using the resources you have in your countries, because, you know, generally we see in India, Pakistan, there is a shortage of limestone and an abundance of clay materials. So if you can make the balance of producing cement more towards clay and less use of limestone, you have a much more efficient use of resources and capacity to extend capacity.
Thank you very much, Karen, for your question, answers, and for your keynote addresses. We need to move on now, and you will be here with us. So if there are any questions coming in the question and answer box, if you can answer that also. The next speaker is Professor Ravindra Gettu. Professor Ravindra Gettu he was the Dean of Industrial Consultant Sponsored Research, and he is a professor at the Department of Civil Engineering at the Indian Institute of Technology, Madras. His areas of research has been in the areas of fracture mechanics of concretes, non-linear behavior of cement-based materials, fiber-reinforced self-compacting concretes, and more recently, he is wholeheartedly devoting himself into sustainability of cements and concretes. I've been privileged he is one of my most beloved professors. We share quite a lot of common thoughts and common goals also. So over to you. It's always a pleasure to hear from you, Gettu, sir. So over to you, sir.
Thank you, Somen. It's thanks to the organizers for having me here. It's certainly a pleasure. I would start by thanking Karen for a very good overview of what is happening with LC3. She has provided amazing leadership and brought this to a stage where we can use it in day-to-day construction. And as far as India is concerned, I think we are LC3 ready. We have done a lot of work at IIT Madras, has been informed, and we would be glad to help anyone who needs our assistance in taking it to a project on site. So I will share some results on the sustainability assessment that we have done, and also show what is the context of our work. So I'll share the screen. I hope it's visible.
Yes, sir.
Okay. All right. So this is work done basically by my postdoc, Dr. Anusha, who worked on her PhD thesis on life cycle assessment. I belong to the group on technologies for low carbon and lean construction, which is headed by Professor Manu Santanam, and you will hear from him in a few minutes. So to tell you a little bit about why we got into this or why we are working on this, our interests are in technologies for low carbon and lean construction, where we are looking at different types of waste material. We want to reduce process waste also. That is where the lean comes in. And this, we believe, will lead to sustainable construction. So we are looking at different type of waste. We had one question about agro waste also. So this is also something we are working on. And our approach is a systems thinking approach. We are not just looking at providing solutions, but we are also going all the way to giving a fundamental background, developing technology, and even looking at policy. And some issues were already brought up regarding codes and so on. So we have a large group. We have about 30 people working in this TLC2 initiative. And if there are more questions on this, we can take up. And our approach always has been to look at the whole life cycle. We want to look at the life cycle approach. We are looking at the raw materials, the supply chain, going on to design. We have also done some demonstrators. We've done one building on LC3 also, and that Professor Manu can give more details if needed. Our emphasis is very much on durability. See, I think sustainability cannot be thought of without durability. And then we are also looking at the end of life cycle and the reuse of materials. So we are looking at a test bed where we are seeing if there is a material that needs to be looked at, we can get the fundamentals and see how to take it into practice so that sustainability is always kept in mind. So when we talk about sustainability, what are the things that I would like to talk about? The impacts we have generally considered are carbon dioxide emissions and embodied energy. There are more impacts that we can look at, but for cement and concrete, these are the two crucial ones that we have to keep in mind. And remember also, energy also means cost. The more fuel we need, the cost also increases. So it is not only in terms of sustainability, environmental impact, but also in terms of cost that we have an impact on when embodied energy decreases. So when we use a tool called life cycle assessment, this is very well established from all over the world. We have to define the system because we can look at only the plant, or we can look at only the kiln, or the whole environment. So here I will show you results on what we call ground to gate, or mine to gate, or cradle to gate. That means we are looking at all the environmental impacts from the mining up to the gate of the plant, be it the cement plant or the concrete plant. And we collect the data directly from the plants. We are not using a database. See, a lot of people use databases like international ones, and these have data from, say, Europe or Switzerland, and that is very obviously not applicable to Indian conditions. So we need Indian data. And that we put in a lot of effort going to plants. And I would like more companies to come forward so that we can get more data from plants. And then we convert this inventory data to the impacts, and we can also consider other things. Like I told you, durability is very important. So what we are thinking of, or what our framework is, we take the embodied energy, we take the environmental impact, we also combine with strength, workability, and carbon and durability to give a complete indication of the sustainability. So this is our sustainability approach, and I'll show you some examples in the next few slides. So we did a lot of case studies. We went to a lot of plants. This is a list of different plants that we have visited and got data from. I will focus just on one so that in the limited time, I'll give you some examples. So this is from a plant in Nandyal in Andhra Pradesh, where there is production of OPC Portland slag cement, PSC, and GGBS. And I'll show you some data. And we are also going to assume hypothetically that LC3 is made there. So this is a state-of-the-art plant, and they're already making OPC and PSC. And we are going to assume for our calculations that they are ready to make LC3 and what would be the impact comparatively of these different cements made there. Okay, but we have done it for the other plants also, but I'm just showing you results for one plant. So to start with, we have to consider all the processes that go into making cement. So this is very tedious, but it has to be done. We just cannot go blindly to some database and take it without knowing what are the materials being used, what are the processes, distances applicable to the Indian plant in question. So this means that we have to see where the electricity is coming from. Is it from the grid or a dedicated plant? What are all the fuels needed? Because there could be alternative fuels that are being used, which would vary from plant to plant. Then we have to look at all the raw materials. It is not just the limestone, but in this case, for example, they are using some laterite, some red mud, and some flue dust. So all this has to go in. We have to know how many kilograms of each, what is the distance traveled by each of these materials. So we need to work in close cooperation with the plant to get the data right. Then once all this is collected, it has to go into the processing to prepare the raw meal, and then it has to go into the kiln, and then we'll have to know what is the energy requirement of the kiln. Then we get the clinker. The clinker is combined with gypsum to get OPC. In this case, we also have PSC production, so you can see the numbers. So just in this plant as a reference, for every ton of OPC, 855 kgs of CO2 is emitted, 3,900 megajoules of energy is required. Okay, so that is the reference. Now we want to see what happens if you have other types of admixtures, the other types of cement, particularly LC3 being made in the same plant. So let's see the numbers. So here I have compared the ordinary Portland cement. This is the ground to gate calculation. Okay, previously I had shown just what is happening in the plant. This is the ground to gate calculation of cement. 910 kgs of cement is associated with the production of ordinary Portland cement. 910 kg of CO2 is emitted. Most of it is coming from the clinker. You see on the right, I have the breakup for clinker. 920 kgs of CO2 for every ton of clinker is what we are emitting. Most of it comes from the gray part. The gray part is direct emissions from limestone. Okay, and then you have some part which is coming from the fossil fuels, pet coke, and so on. So all this is coming from the fuel. So this gray part in this larger diagram is the clinker part. Okay, and you see that as we decrease clinker, the CO2 emissions come down, as is obvious. I have here PPC, slag cement, and LC3. And you find that LC3 shows about 300 kg reduction in the CO2 per ton of cement. It is slightly higher than PSC in this case, but slag is not always available everywhere. So a better comparison is directly with OPC or even PPC. Okay, so you see that it comes out better. There is some part from the clay calcination. There have been questions if that is very significant. And you see it is much less than what is coming from the clinker. It is there, but it is much less than coming from the clinker. And here I have assumed that the OPC has 90 to 95% clinker, PPC has 70 to 75% clinker, PSC 40 to 50%, and the LC3 has 50% clinker. So you clearly see how much there is a reduction in the CO2 emissions when we are looking at cement, comparing LC3 with OPC. Now let's look at energy. I had already mentioned energy is also cost. Energy is use of raw materials. And we see this significant reduction as we go to blended cements, from OPC being about 6,000 megajoules per ton of cement, being the embodied energy, the energy required to produce this, And as we go to lower and lower clinker, it decreases. With LC3, there is some requirement of calcination, which makes it comparable overall to PPC, but it is significantly less than what is required for OPC. And on the right, you have the breakup for the clinker. So most of the energy in India, in this plant in particular, comes from the burning of pet coke and other fossil fuels. And there is some part which is also coming from the electricity requirement for the grinding and so on. So clearly you see that when we use LC3, we have a huge reduction in the emissions and the energy requirement. Let's look at concrete. So for concrete, again, we have to do the same thing. The life cycle assessment goes on a similar procedure where we have to look at all the processes. So here it means that we have to look at the cement production, the aggregate production, and water requirement, and the final mixing and transportation. Electricity mix also comes in. So again, we have to do all these calculations. We have to get the data on how much material is used in each mix and what are the distances it has traveled. So I'll show you data for different types of concrete. I'll show you M30 concrete made with OPC, fly ash addition, and LC3. Okay. In this case, the M30 concrete required about 310 kg of the binder of the cement, and the water binder ratio was varied to get this strength. We also made a higher grade concrete, M50 concrete, with different binder contents needed for this M50 grade. And then there is a common mix which has the same binder content, but giving obviously different strengths because the binder is fixed here. All these cases, the slump was about 100 mm. So these are workable concretes. These can be used at the sites. So I'll show you some results. So on the left, you have the energy consumed. On the right, you have the CO2. And clearly you see that if you compare with OPC, PPC and LC3 are coming out much, much better in terms of energy as well as carbon dioxide. There is a slight increase as you increase the grade, but that is okay because you'll use less amount of M50 anyway. Okay, so clearly what benefit we see in the cement also is there in the concrete. So let me go on to bring in durability also. When we are talking about sustainability, I said that durability and other parameters are important. So we are considering two types of indicators. One is the energy intensity index, which combines the effect of energy and mechanical integrity. And you can see that it also reflects well the improvement in the structural level that we will see when compressive strength increases. If we look at only the energy, it looks as if a higher grade concrete requires more energy, will have more emissions. So that is why what we have done is divided by the compressive strength. So you see here that the energy intensity index decreases as we increase strength because the efficiency becomes better. Very importantly, we have defined a second set of indicators called apathy indices, which divides the carbon footprint by a service life parameter. Okay, and this could vary from depending on the attack you have. So say if you have chloride attack, chloride ingress is governing the durability. Then the apathy index is the carbon footprint divided by a factor that depends on the chloride diffusion. You see the chloride diffusion coefficient here. So with this, we have brought in on one side the energy, the mechanical integrity, and on the other side, we are bringing in carbon emissions and the durability. So with this, we believe that we can check, we can see if a material, a concrete is more sustainable or not. So the concretes that I've discussed before are plotted here. Okay, so on the y-axis, I have the apathy index. Apathy index definition is given here. On the x-axis, I have the energy intensity and definition is given here. Whatever is going in this direction, closest to the origin, we consider is more sustainable. And clearly, you see that LC3 falls here. Out of all these, very clearly, the LC3 comes out most sustainable, followed by fly ash, followed by the OPC concretes. So if you look only at M30, so all these three are M30. They satisfy your requirements from the design point of view. They're all workable. Very clearly, the M30 made with LC3 is more sustainable than the other two. What about higher grade concrete? If you go to higher grade concrete, it is more and more sustainable, because for the same strength, for the same cubic meter, you're getting more strength. Okay, so it becomes even better. And the common mixes also have the same thing. So very clearly, higher SEM content, lower clinker content, we can get more sustainability, and especially under chloride attack, LC3 comes out very, very well. So I'll stop there. Thank you very much. I'd like to thank all the cement companies which have helped. Invitation is open for other cement companies to also come forward so we can get more data and show how the blended cements, particularly the LC3, is very beneficial. Thank you, and I'll be glad to answer questions.
Thank you, Professor Gettu. Thank you very, very much. There are a couple of questions here, if you can look at this.
Okay, so I'm looking at the Q&A. So Javed is asking, do we have admixture compatibility complexities? So as I have said, Javed, we did not have any problems LC3 concretes. We could get a slump of 100 mm very easily. So we can help further if somebody has difficulties, but I don't see any issues at all. There are admixtures being particularly developed for LC3, but I don't think that is an issue or a showstopper right now. Then in the chat, I don't know if there's anything.
Techno-commercial, they're asking, Javed is again asking, what is the techno-commercial feasibility of using admixtures?
See, again, I don't think it's an issue. The costs always vary depending on the type of admixture you use and the quantity. But I don't think when we are looking at the entire project, I don't think this is a showstopper really. I don't think that there's something that we should worry about.
Before we move on, next is my present. Before we move on, sir, one question here is that the various state governments in India, you know, the state governments, if all of the state governments are looking at going carbon neutral by 2047, most of the states have taken up already. Sikkim has gone carbon neutral. Ladakh, we were there last week. Ladakh has already announced that it is going to do a carbon neutral development. Now, and the state of Bihar is also looking at how do you go carbon neutral by 2047. And one of the areas that they are a little bit not concerned, but are looking at putting more emphasis on the cement industries. Transport sector, energy and cement. These are the three major things. So how do you see this, that what are the recommendations? Can we also work with the state governments in doing the kind of studies that you have done here, and then recommending to the state government that this is the kind of low carbon pathway or to reduce your carbon footprint? These are the various things that you need to look at.
Yeah, thank you so much. I think we have to work with the state government. See, the biggest problem are the tender conditions. Tender specifications. So I think we have to come up with model specifications. We went through this when we looked at fly ash, and we need some demonstration projects. So it will not automatically happen. In most cases in India, they just copy the specifications in previous projects. And when there is something new, it becomes very difficult to implement. So we have to handhold, we have to participate in committees before a project. See, after a project, it becomes too late. And the fact that state governments want to go zero carbon is really positive. We should talk to them about changing tender conditions. We should have ways of bringing in sustainability, especially low carbon footprint, low energy and durability. See, we cannot sacrifice durability. This is something that I'm always worried about when we have people talking about zero carbon. It can be zero carbon, but if it does not last for a long time, you will have a lot of trouble. Okay. So there is one question from Kuldeep on durability effect. So it is very, very important. So Kuldeep, I showed you results on chloride attack. Certainly, in terms of chloride attack, LC3 is much, much better. in terms of giving the resistance against chloride attack. Now, other types of attack also we are studying. Right now, I don't have time to present all the results, but we can discuss it further and you can reach out to us. We can give you results. We have looked at different things. We have looked at carbonation, we've looked at sulfate attack, we've looked at acid attack. So we can certainly provide more data or help if there is a particular application. But let us talk about application before we talk about very general durability. Every type of attack is not going to occur in every application. So we have to be sure about the application, or first we have to think about application before we talk about durability.
Thank you, sir, very, very much. And there will be some question and answers that will be coming if you can answer them. Sure. Let me move on. Move on to my presentation. What I am. Can everybody see this?
Yes.
Okay. So what I am going to present here is to talk about a little bit on the resource availability for producing cements, very, very specifically looking at India. A typical problem with India is that maximum of our production is based on either fly ash based cement and little bit to slag cements, but still we produce OPC. Now, what is the kind of condition that we are looking at going into the future? So if you see the ecological footprint in the globally, at right now people don't believe this, but we are now consuming around 1.7 times. This is by 2010 we were 1.5 times, and right now we are consuming 1.7 times the total resources that is there that the earth can produce. And if this is the kind of scenario that is going there, with a business as usual scenario, by 2050, we will need at least 3 times 3 Earths to supplement us. And if we need to reduce this, then there is if you see that yellow curve, there's a drastic change that is necessary. Now, let us go back, let us see what is the status of the construction minerals. In terms of resource use, construction mineral, there is an accelerated growth of resource use in the last 2 decades. It started not last 1980, last 5 decades, I would say. It has just accelerated like anything. And over the last 2 decades, the curve is almost horizontal. So that means we are extracting a huge amount of construction materials and using it for building, for using it in various other kind of works. Going into the status of the cement industry, in the Indian cement industry, very, very specifically, we are the second largest after China, second largest producer of cement, which approximately it is around 7% of the global demand. In financial year 2022, we produced around 381 million tons of cement. It was a little bit depressing figure. We should have produced more, but due to the pandemic, COVID-19 pandemic, the construction was not picking up in a much faster rate. But this was the kind of figure. And we have, as per the Planning Commission or the Niti Aayog that we have an year-on-year growth of around 12%, which is at least going to be sustaining for the next 5 to 10 years. This whole demand of cement is fueled by the kind of construction that we are doing, the push by the government, push by the private sector, the public sector on 3 things. One is on housing, because we are shortage of homes. The huge amount of infrastructure work that is going on, building of roads, airports, railways, all other things. And of course, modernization or urbanization of tier 2 or tier 3 cities. That is where the maximum demand of cement is coming. And this is going to sustain over what our prediction says that at least in the next 20 to 30 years. This is one of we are proud to say that we produce and cement industries are there with us. We say that we produce one of the greenest cement in the world. This is mainly due to the amount of fly ash that we have and the slag we have. And in our cases in India, around 73%, only around 27% is OPC or ordinary Portland cement, and the rest 73% is the blended cements. And out of this 73, around 63% is produced from fly ash based cement, and only around 9% is Portland slag cements. So that's the status of, but still, even if you say that these are the kind of high demand where we are the greenest cement, but still we contribute to around 7% of the total CO2 emissions of the country. So we say on one hand, we are the greenest cement production, but on the other hand, well, it is not so. The absolute figures doesn't look very, very rosy. And this is the way that the carbon emissions has been increased. It has been tracked over the last, from 1960, over the 1960 to 1978, 80s, 2 decades, it was very low. And after that, over the last two decades, it has just shot up. There is, in the year 2020, there is a shortfall. There's a reduction by around 14%, but it was due to COVID. But still, even if it is 14%, still we produced roughly around 150 million tons of CO2 in the year 2020 alone. And with the kind of figures that is coming up right now in 2022-23, we are going to cross more than 160 million tons of CO2. So if that is the kind of condition, let us now look at a little bit on the growth forecast. This is figures taken from WBCSD, World Business Council for Sustainable Development. They had previously given higher figures, but then they have toned it down. And this very well goes with the figures of Niti Aayog, what the Planning Commission has given. Because after 2035 till 2035, there will be an accelerated growth, and after that, the growth will be linear. But still, this projection is based on 3 major cement types. One is, of course, the Portland cement, the fly ash based cement, and the slag cement. Now, if that is so, if Portland, and I showed it to you previously, that 63% will be the fly ash based or the PPC based cement. Now, if that is a situation that it really, we'd like to point out, come to the question of, do we have enough fly ash? Because with the emphasis on the country, on moving, or not only the country, but the whole world, in moving away from fossil fuels, India also is looking at reducing its energy demand from thermal energy to more renewable, and we have by 2030 that we will be producing roughly around 50% of energy demand will be coming from renewable resources. That's the pledge of the government that we have. Now, if you see a little bit on, so that means that if we are moving from thermal energy to more renewable energy, then the fly ash situation, the fly ash availability is going to reduce. So there are 2 questions here. Number 1 is whether we will have, at present, do we have enough fly ash? And in the second part is going future, will we have enough fly ash to produce that the Portland or the PPC cement, PPC. This is figures taken from the Central Electricity Authority. They publish annual fly ash utilization report. And what has been coming up showing is that of the total fly ash that we generate, around 90% we have utilized or we are utilizing. This is year-on-year report. And if you see the amount, the fly ash that is being used in cement production over the last couple of years, 5 years, 6 years, it has not increased much. We had been talking to cement industries. The major reason, well, the industries are there, they will be able to give much accurate figures, but whatever the discussions that we are having is that the cost of fly ash is becoming every day, day by day, it is increasing. The cost of transportation of fly ash is increasing. Basically, the cost of procurement of fly ash is increasing. And in certain cases, in certain areas, you don't have fly ash. So what we have done is we have still done a projection and say that by 2050, we will be having around 150 million tons of fly ash to be dedicated for the cement production. Now, if that brings also a question, what we mapped is that if 90% is the fly ash that is being already utilized, what is its status in the states? This figure gives you of the dark red spots, states that you see marked, except Madhya Pradesh and Chhattisgarh. These are the states where it is fly ash utilization is more than 80%. In certain cases, it is 100%. In certain cases, the report says that it is more than 100% because you are utilizing some of the legacy ashes also. The white states, they are especially in Jammu, Kashmir or Ladakh or in the Northeast, you don't produce any, you don't have thermal power plants. And in the other states like Madhya Pradesh and Chhattisgarh and other states, the fly ash, still there is some amount of fly ash to be used. Now, and with the kind of emphasis by the ministries, by the government on utilizing of ash, because they have now enacted a rule, notification that if you are not utilizing your ash, then you will have to pay a fine of more than 1,000 rupees per ton of fly ash that you are dumping. Now, if this is the kind of availability of fly ash scenario, let me plot the cement plants on top of this. The blue dots that you see, those are grinding units, and the green dots that are there, these are integrated cement plants. So still, if you see in Madhya Pradesh, that area, the central part, still in that area, there is fly ash is available. So it makes much more sense to look at PPC-based cements. But in other areas, especially in the Indo-Gangetic plain of Punjab, Haryana, Uttar Pradesh, Bihar, even Bengal, where you have huge amount of thermal power plants also, and there is a high demand of cement, what are we going to do? This is a thing that needs to be discussed with the industry. We need to sit down and think it through also. I'm not presenting any solution here, but this is the true picture, what the analysis that we have done, that I am putting it. Now, if this is the growth forecast based on the previous kind of, if we don't have enough fly ash and the kind of projections that we did for consumption of fly ash by the cement industry, PSC slag cement, because slag is not much, so that is going to remain at a 9%. PPC is going to increase. PPC again will be a stagnant growth because you don't have enough fly ash. But if we have to meet the growing cement demand, then till date, I'm not talking about LC3, but till date, we don't have any other thing other than falling back into OPC. And if we go into fall back into OPC, that means your CO2 emissions, as Professor Gettu already mentioned, 910 kg of CO2 per ton of cement. So the emission factor increases like anything. So one of the material that Professor Scrivner also has pointed out is available in plenty is clay. We have been, along with IIT Delhi, along with various other IIT Madras and various other institutes, we have been working on mapping of clays across the country, and we are really, it is a surprise to us also that clay is available in massive quantities, and this clay is not reported in the Indian Bureau of Mines or in the published with the GSI, because when the data that the Indian Bureau of Mines or the ministry gives, that is for clays which are suitable for ceramic use or suitable for refractory, paint, paper industry, which has very high kaolinitic content. The clay that we are talking about in a cement plant is any clays which has kaolin content of around 40% is suitable. And that clay is available in plenty. We have been doing surveys across the country. Anywhere, we have still, till date, we have not failed in looking at this. So a blend of calcined clay and limestone, as Professor Scrivner pointed out, it's very interesting, and that brings to the question of LC3. So work in India is not only in India, but it is going on across the globe. And we are working not only with cement companies, but also with government agencies in looking at standards, working with cement companies in undertaking clay feasibility studies, whether you have clay, and if you have clay, where it is, and if we know that where it is it suitable for use it in cements? And then working for looking at small pilot scale demonstration and evaluating the quality, including the kind of the sustainability analysis that Professor Gettu has also mentioned. This is a more realistic solution that we think that we are going to grow. And mind you, here what I'm not saying that the PSC is going to remain. And this is our kind of solution that we say. The Portland slag cement that is going to remain, that you will be, that nobody will be able to replace it. LC3, with the standards being published in the next couple of months, LC3 is going to pick up. Initially, the rate will be slow, but then within the next couple of 10 years, it is going to pick up. And then it is going to be remain stable. Fly ash-based cements will be there. LC3 will replace some amount of OPC. And in certain cases, yes, it will be a preferred choice of cement companies to look also instead of PPC. So this is the growth projections that we say. And if that is the kind of a situation, then we will be contributing to around between 10 to 15% of the NDC, the targets that the government has set itself. Now, last slide, what are the sustainability benefits? Yes, if we are moving towards LC3, we don't have a choice. Either we do fly ash based cement or we move into LC3. Fly ash is not there, so we don't have a choice but to move towards LC3, and it is becoming critical. It will be critical in helping the country to meet its NDC targets, both in an 2030 and beyond 2070, where we have committed that we are going to go carbon neutral also. LC3, of course, always it is low carbon. It has a potential of reduction of around 40% CO2 emission. And in certain cases, what people have also reported is that it can even go beyond 40%. Because when you are calcining the clay as a fuel, if you can use renewable biomass, because the temperature is low, around 800 degrees centigrade, we have done trials with it. We were successful of using waste biomass. And if you can use that, then the amount of emissions is also going to reduce higher than 40%. And you can save more than that. Resource efficient, yes, of course, it consumes the composition that we have. 15% of crushed limestone that we use, that is of not and cement grade limestone, it is now being waste. We don't call it a waste. We say that it is a non-commercial grade material. And the calcined clay that we are using here, that is also not of the ceramic. That's a waste clay. Professor Scrivner already pointed that out. So in that total mix, we have roughly around 45% of non-cement grade or non-commercial grade raw materials. And this is if we are using up waste materials and using up the waste limestone, then it is going to help us in preserving our land. It is depending upon your transportation of the clay from where you are bringing it. The cost effectiveness varies between 20 to 30% also. And it is not a very capital intensive kind of modification. You don't need to set up, one question was that, do we need to set up a greenfield plant? You don't need to set up a greenfield plant. You can easily accommodate within your existing plant. And of course, this is going to help us in transiting transition towards a green economy, where fly ash is going to be a constraint. So what we look at is, these are some of the areas that we still need to work on. Research needs to be continued. Fly ash cements, blast cements came around 40 years ago. But still there is a huge amount of research going on in fly ash PPC. So the research has to be going on continuously, and it has to be accelerated, what we call it as a mission mode. Now we are looking at the cement, then we need to look at the concretes. For the companies, if we can also look at LC3, and that's a kind of question that I also had in, what is the incentive of a cement company to go into LC3? Because cement companies are basically there to do business. Now, if we can save CO2 emissions, and if can also be traded for carbon credits, India now has a carbon trading platform. If you can trade it for carbon credits, then at least the companies get financially. Some sort of green financing needs to be available to small and medium companies for adopting greener or cleaner technologies. And we need to work on the market imperatives, which is increasing the visibility of, right now we have worked on the supply side. Now we need to work on the demand side, where we increase the visibility of LC3. Who is going to buy, especially among the architects, the builders who are going to use it, and looking at including LC3 in all the green rating systems that we have. In terms of the government, well, the LC3 standards has been approved, but now we need to fast track the publication of this. And if we need to work with the government in notification of LC3 in public and public procurement and in public construction. Thank you very much. I see some questions also. Whenever the questions, I will try to answer them. But let me now, since I have already overshot my time, let me go to Professor Manu Santhanam.
Okay, yes, please.
So, Professor Manu Santhanam is, well, I am associated with him for the last couple of years, one of my dearest friends. He is a professor in the Building Technology and Construction Management Division in the Department of Civil Engineering, and he is also has been the Associate Dean for Industrial Consultants and Sponsored Research at IIT Madras. His research domain covered the cement chemistry and characterization of concretes, including destructive and non-destructive testing. And in recent years, Manu is also working very heavily on 3D concrete, 3D printing of concretes, concrete durability, and use of supplementary cementitious materials. Over to Manu.
Thank you, Somit. It's indeed a pleasure to interact with all of you today. So let me quickly share my presentation. Are you able to see the full screen?
Yeah, please make it full screen.
It's not full screen?
No.
Okay, 1 minute. I'm using two screens for this problem.
Yeah, that's an issue problem that we have.
How about now?
Yes, perfect.
Right. So again, good morning to all of you. I'm going to talk in this lecture about field applications of LC3. So as Professor Karen had already pointed out, one of the first applications that we did with a commercial LC3 that was produced in not very ideal circumstances, that was the building in Jhansi. But since then, we have had very good industrial scale productions of LC3. And we've been applying them for various different applications of concrete technology. Here, I'm going to demonstrate a couple of applications that we basically took on because of the extremely good nature of LC3 concrete with respect to chloride exposure. So I'm going to talk about two applications here. But before I go there, of course, let me reiterate, LC3, primarily what we're talking about here is a blend of 50% cement clinker with 30% calcined clay. 15% limestone and 5% gypsum. So essentially it's a 45 or rather 50% replacement overall of the cement clinker with the mixture of calcined clay and limestone. Of course, gypsum has to be modified based upon the chemistry, so to ensure that we get the best performance from LC3. Generally, you may also see in some examples that you have from Cuba that they've also looked at it as a complete pozzolanic cement where 65% clinker is used. Calcined clay to limestone ratio typically in LC3 is 2:1. And in some instances, it turns out that even 1:1 can be permitted because not all of the calcined clay gets a chance to actually react. The reactions primarily which lead to the unique behavior of LC3 include, of course, among other things, they eliminate from the calcined clay and the carbonate from the limestone. They form additional compounds like carboaluminates, which are very useful in filling up the pores and ensuring that you have a very low permeability in the concrete. Then, of course, the calcined clay, like any other pozzolan, like fly ash or silica fume, can continue to react with calcium hydroxide and lead to the formation of calcium silicate hydrate, the typical pozzolanic reaction that you expect. Now, LC3 concretes, we've had years of research now. Overall, I think from IIT Delhi and Madras and Tara together, we've produced data in India for the last nearly 8 years. And with this data, we are quite confident that LC3 performs excellently in chloride environments, even better than fly ash and slag. And the main reason is basically the composition and the small size of the pores, composition of the hydrated products, and the small size of pores that we have in LC3-based concrete. So based on this, what we have concluded is that LC3 is an ideal choice for a marine environment where we expect a lot of chloride-related problems, especially corrosion. So the current study essentially was to look at the use of LC3 in reinforced concrete structural elements of a small shed that we had conducted, which we have constructed in the Central Institute of Brackish Water Aquaculture. And this is very close to the coast, only about 400 meters away from the coast. And we wanted to monitor the compressive strength and durability of concrete, which is only cured for about 7 days on site, and then, of course, exposed to the natural conditions. And we are continuing to monitor this. We'll be doing this over a long period of time. And this will continue for a time period of nearly 5 to 10 years. So this is the demonstration building. It's a very simple building. It's a smaller version of the house that you saw in Jhansi. That was actually a proper reinforced concrete house, but here we only wanted to have the reinforced concrete structural elements like columns and beams made with LC3. The walls, of course, are regular brick walls, but the plastering also has been done with LC3. So we are here obviously looking at an entire structure made with LC3 cement. The site location, as I said, it's very close to the coast. So you can see from this picture here, let me just use the pointer. You can see the picture. This is actually the sea here, the Bay of Bengal, and the location of the site is somewhere in this place here. So it's about 400 meters away from the actual coast, but there's channels of salt water that are actually inundating the site from time to time. So when it rains or when it when it's high tide, you get a lot of water here, and the entire site becomes inundated with salt water. So you can imagine that the conditions are quite severe with respect to the exposure that you have for the concrete structure. Now, as far as the site logistic issues are concerned, it was not very easy to work here. As you can see from this picture here, sorry. Yeah, we were using a very rudimentary type of a concrete mixer, basic tilting drum type mixer. The site where we had to actually do the concrete production was quite different from the actual location where the concrete was to be delivered. And you can see people here carrying concrete in small containers from the point where we were actually mixing to the site, which was located slightly further away. We had to actually cross this bridge. So the site where we mixed the concrete was somewhere around here. We had to take the concrete on foot across this bridge and to this location where you can see that building, which is completed. So overall, the transport time, of course, transport not by a vehicle, but by people carrying containers of concrete, the transport time was about 20 to 25 minutes. And many instances with LC3 concrete will tell you that workability retention with calcined clay-based concretes is sometimes a challenge. You have to design for it. You can do it, but it's quite challenging. So we had to ensure that we had adequate workability at the time of delivery of the concrete at the location. You can see the kind of concrete that we produced. We had a fairly good slump, about 110 millimeters after 2 hours. So we designed the concrete with a sufficiently high superplasticizer dosage to achieve the right level of slump. You can see the final site mixture design was a little bit different than what we started off in the laboratory. That's because of these issues, the challenges that we had with the transportation and so on. So here, the exposure condition, as I said, is very severe. It's not, of course, directly in the tidal zone, or rather not subjected to the splashing of the waves and all that, but still the location is quite in a very difficult condition. So here you can see that the backwaters basically can inundate this entire site. You can see during the time of construction, the kind of inundation that has actually happened in this picture. And the groundwater here, because of this inundation, has a very high chloride content, 17,000 milligram per liter, and about 1,500 milligram per liter of sulfate. So this is the condition in which the structure is actually standing. You can see that we have embedded some columns in the ground for a long-term study about how the concrete deteriorates. All the other concretes, even this embedded columns are structural reinforced concrete. So we know that we can understand whether corrosion is happening or not. We also have concrete specimens that have been stored alongside after 7 days of curing. And we are taking specimens from here and bringing to the lab and testing them from time to time. As you can see, up to 90 days, all the tests are really good in terms of very high resistivities that one can expect from such concrete. You also get very low chloride permeability as measured by the RCPT test, and extremely low chloride migration coefficient, which are typical of high performance concrete. You can see these numbers are typical of high performance concrete. And this is actually an earlier 35 megapascal grade concrete. You can see it's about 42 MPa at 90 days. So it's a 30 to 35 megapascal grade concrete. And we are able to produce such low chloride migration coefficients. That clearly tells you the excellent performance one can expect from concrete, which is made with LC3. And even sorptivity and water porosity are in a good to very good sort of a range. Again, these are samples that are stored on site. So we also we brought them back to the lab and tested them at 28 days. As you can see, obviously, they are producing results that are excellent. And very early stages, we also did not get any carbonation in these specimens. Now, there's another site where we actually used LC3, and this is a very different site. It's actually a highly controlled concrete manufacturing site where they're using concrete to manufacture tetrapods to make this breakwater structure. The breakwater structure is going to be nearly 7 kilometers long. And of course, since it is not reinforced, the concrete is only it's a plain concrete structure. That's why I put this design life of 10,000 years, because there's no steel to really corrode. As long as the concrete can withstand the action of the splashing of the seawater and any surface scaling, it's going to last forever. It's like a regular rock, right? Like a regular stone, which has been embedded in seawater. So here, it was a slightly different application. And you can see the number of tetrapods that they have in this site. It's a stacking yard. The tetrapods come in different sizes, 2 tons to 20 tons, very large variation. And the tetrapod is expected to be placed in this location where it's going to be subjected to a constant splashing of the seawater and chloride intrusion. So we will obviously monitor the stability of this material from time to time to ensure that we are getting the best performance out of this LC2 tetrapods. Here, again, very vast amounts of concrete are needed. You can imagine a tetrapod of 20-ton size, how many cubic meters of concrete it would take to really fill up that 20 tons. So 1 cubic meter is about 2.5 tons. So there's about 8 cubic meters of concrete in 1 tetrapod. And so many of these tetrapods, if you have to have a 7-kilometer long backwater, you can imagine the extent of concrete that is required and amount of cement that can be saved by utilizing something like LC2 or LC3. So in this case, we used LC2, which is a combination of limestone and calcined clay. And here, the cement which was being used was actually a Portland pozzolan cement, because they had some issues with overall heat of hydration. And because of that, PPC was being used on this site. So in fact, here, our cement combination is cement, fly ash, limestone, calcined clay. It's actually a quaternary combination. We have 4 different types of cementing materials present inside. 350 kilograms of cement and free water of 140, which leads to 1.4 free water to cement ratio. And with this, of course, we are monitoring various different qualities of the concrete with time. And compressive strength at 28 days that we obtained was about 45 megapascals, much more than their requirement of 37 megapascals. And even at one day, sufficient compressive strength of 15 megapascals was available, because that is required to remove the molds and then handle or lift the tetrapods and bring it to the stacking yard. And this is the team with my students and the people from L&T who are there to execute this project. L&T is really interested in taking this forward. They are very excited about using LC3, especially in these kinds of applications. So just to conclude, LC2-based concrete or LC3-based concrete can be a viable alternative for large-scale construction, subjected to chloride exposure, very severe chloride exposure, and even in site conditions that demand long workability retention. In both those sites that I showed you, we got very good retention for at least 2 hours, and that was simple, good enough to actually execute those projects. There are obvious choices where we don't really have a problem of workability retention, for instance, pavements, and even in 3D printing, where actually the loss in workability can be quite a very positive aspect. And I can show you some examples of 3D printing with LC3 concrete. As you can see, the concrete with LC3 can be printed fairly quickly without really stopping, and it provides an excellent buildable mix, which is able to produce 1 meter tall columns in 20 minutes. And that's what we had done with LC3 and 3D printing here. You can see with LC3, we are also able to increase the aggregate amount in concrete, which is being 3D printed. So that's a very big positive with LC3 based systems. So again, this is just an additional example of where LC3 can be applied, but primarily we are obviously concentrating on looking at LC3 and chloride related environments. That's where the most potential with LC3 can be derived. So thank you all very much. Thank you so much.
Thank you. Thank you very much, Manu. Before, just 2 quick questions that has come up, if you can have time to answer them quickly. Number 1 was, have there been any tests using LC3 based concrete for seawalls?
Have there been tests with LC3 based concrete for seawalls?
Yes. This has been from Paul from Fiji.
Okay. No, we have not done tests with seawalls, but I expect the performance to be quite similar to what we expect with the tetrapods, because the environment will be quite similar to that. We will have a constant splashing of seawater, and the concrete has to be highly abrasion resistant. We have also tested abrasion resistance in the lab under the very strict regime of the ASTM test, which deals with hydraulic abrasion, which is more related to dam-related structures. So even in that, it performs really excellently. So I can expect that in seawater type of environment, there should not be any problem. With respect to corrosion, of course, you can see the very low chloride migration rates that we actually have in such concretes can lead to excellent performance with respect to seawalls or any structures on the coast.
One last question was the presentation that you showed. It was from the seawater. Now there are other kind of applications where there are harsh conditions, like, for example, we were there in Ladakh last week.
Correct.
Where, Ladakh, it's a dry, cold desert.
Correct.
There, the concrete doesn't last for quite a long time. So the question that was asked was that, will the performance of concrete be improved in those kind of harsh conditions?
So yeah, we had done a demonstration structure like a pavement in the harsh conditions in Ladakh, and we have monitored it for about 3 years now, and it seems to have worked quite well. What you of course need to do in an environment like that is to design the concrete to resist against freezing and thawing. So here 2 things can help. One, of course, use of air entrainment in concrete is absolutely a regular practice that is done for any environment related to freezing and thawing. But the other thing is, with the very small porosity that you have in LC3 concrete, water may find it very difficult to freeze inside such concrete. So even without air entrainment, LC3 concrete may still be good enough to resist freezing and thawing damage.
Thank you. Thank you very much. Thank you, Manu, very much. Moving on, let's hear from the industries who will be manufacturing and producing this cement. So first we have Mr. Raju Goel from UltraTech Cements. May I introduce Mr. Raju Goel? Currently, Mr. Raju is working as President and Chief Technical Officer in UltraTech Cements. He is having experience in formulating and implementing the growth strategy of businesses, creating innovations, looking at research and development roadmap for sustaining market, and of course, the cost leadership in reducing the costs. He has been a pioneer leader in identifying the business drivers for technology solutions, and he's associated with, before he joined Ultratech, he was associated with large number of cement companies abroad, especially, and over the last 3 years, he's there at Ultratech. Over to Raju Goel, sir.
Thank you, Mr. Somen, for the wonderful introduction, and good morning to almost good afternoon to all everybody, just by the 30 seconds. And it was a pleasure to hear the stalwart of the material science and the product which we have seen in the past few hours. I will just share you the thought process from the cement industries and what the cement industry can look and what they can be focusing, and how I feel that it should be considered to take its sustainability roadmap and build the roadmap for the industry as well as the plant or as well as the company. I'll just share some thoughts. Let me put some of my slides here. So please let me know if you can see my slides.
Sir, we can see it. Can you please put it in
I will do that.
screen?
I will do that. I will do that. Can you see now?
Yeah, but this is the operation slide. You have one.
Yeah, this is the first one. Yes.
Perfect, sir.
I just wanted to share with you what cement industry thought process can be for towards our sustainability journey in cement industry. So what I feel that these are the 5 areas we need to be having a focus as per the cement industry point of view. One is coming the operation, because as you know that cement industry is a very energy intensive raw material as well as the fuel in thermal side, very intensive industry. So operations becomes very, very important, how to reduce the CO2 footprint and how to optimize the operations to minimize the impact on the sustainability. And second point, I'll say that energy, because as we know that thermal and electrical energy is the intensive in this industry, how we have to find the alternatives for that and how we have to substitute the current traditional energies to the new energies or renewable energies in our operations. And third, I will talk about the materials, which is coming to the circular economy. What are the materials? As we all know, about 80 to 90% of the limestone, which is the natural reserves, are used into the cement or clinker production. But again, how we can add the additives and other alternative materials towards to sustainability energy as well as the material and product. And I'll talk about the product, how the products also can be help to build our sustainability roadmap and sustainability journey to go forward. And then last point, I'll discuss about the innovations, because how the technology can take place in our operations. Because if I say that, I may be wrong, by my cement colleague may not be happy to say that, or not agree with me, because last 100 years cement production technology has not been changed. Yes, there is a small changes here and happen this one, preheater to calciner to the different bending technology and things, but not a significant shift is happened in terms of the technology point of view. So innovations can play a very important role in our sustainability journey. So let's talk about our operations improvement. Operation improvement, as I think, if I can say that cement industry in India has much ahead than on the world standard or world operations outside India. They have achieved the significant efficiencies in terms of the power, in terms of the material, in terms of the electricity consumption and things. But still, there is a few things I believe that production and productivity can be further improved by using the digital solutions. That's the reason I put up a first point in this one, because a lot of data is available, a lot of information is available that how to use the digital solutions to improve our productivity overall, which will definitely have the impact on our CO2 footprint reductions on that. Heat consumption, India is doing much better than the rest of the world, but still there is a option how to optimize further by using the different technologies and different equipment and the available solutions to increase or reduce our heat consumption, the power consumption, our cement plants. Clinker factor, one of the things, because as you know that there's a two part of this, because one is our standards, one is our industry. So clinker factor, one of the area which industry is doing quite significantly good, but there's a further area. But given that clinker factor, because availability of the raw materials and availability of all the additive materials or SCMs, this has become sometimes one of the area which we need to look into that. And we discuss the alternative materials in the second part of this. Thermal substitution rate. Right now, if you say that 70% of CO2 is coming from the limestone calcination, 30% coming from the fuel in our clinker production. And if we see that the immediate lever which can be for the fuel substitution, it means we have to use the alternative fuels in terms to reduce the dependency on the conventional or the traditional fuels, which are coal, fuel, petcoke and things. And oil, we have to go for the alternative materials like waste materials, RDF, MSW, biomass and things to increase our thermal substitution rate. Transportation, I put up the transportation. This is not the transportation on the road, but transportation inside the plant, where we have kind of a energy required quite significantly on that. For example, transporting the material from A point to the B point, we can have the mechanical conveying, and we can avoid this all the in-house transport system and things, and what you call this pneumatic conveying systems. This is also one of the area we can see that. But second thing, also look at the community side, because in our all the cement plants around, there's a communities are there. They have quite significant waste product, which is kind of like for example, cow dung and other things, which can be used as a gobar gas plants and things, and how they can also be promoted and things which can link to our operation, and waste can be used in the communities to enhance their CO2 reduction by using the biogas plants or gobar gas plants and some to arrange the help the community also to focus on that. So that's the reason I put in the operational improvements. So focusing on this technology adoptions, upgradations, and digitalization, AL and AI and ML, and optimization takes very important part for to reduce our CO2 footprint in operational space. And adopting the green energies, as I discussed, because we need significant thermal as well as electrical energy, which can be coming from the right now the TPPs or coal-fired power plants, which can be replaced by the WHRS, which can be renewable energy like a solar and wind, and specific thermal energy, especially to be reduced in terms of the consumption point of view, because efficiency of the turbines and things can be further enhanced. And hydrogen and the battery storage is also coming up. This how we have to see that how we can be used into our replacing the traditional energy usage. So digital solution can definitely improve the energy productivity, or losses especially can be reduced. And latest technology in higher efficiency motors, drives, and equipments can be also be the part of that. LED for this, especially in the in-house operations, we can look into the solar systems and LED to reduce our dependency on the traditional energy. So as Ultratech, we have committed about 34% of our total power requirement will be done by the RE and WHRS by 24. And this is the commitment we made for our sustainability things. And then increasing the value from the waste. This is, I think, one of the area which we already discussed, I'm sure in the previous sessions. So corrective and additive materials. When we say corrective additive materials, because other than limestone, we need corrective materials like iron source or alumina source, clay source, how this can be used. The waste material which is produced by the different industries or different processes, not using the natural resources. And other than coming to that ash, which is coming out from the different processes, may not be directly used into the cement production, but can be used in the process somewhere. How this can be 100% zero waste can be coming from the other processes, can be used in our cement processes. Co-processing, when I say co-processing, which is all the waste coming out from the different industry, pharma, agro, and like our dumps and things, where we can use this material as a substitution of our fuel and substitution of our raw materials wherever we can use as a industry. For example, red mud, copper slag, fly ash. I think this is already happening, but other materials which can be used like a phosphogypsum, which is one of the area which we have to see that how we can use that material. And concrete, I think of concrete processing, we can also look into that how to recycled material can be used into our concrete processing, and how it can be used to give the same strength, same quality by using the alternative materials, alternative raw materials which can be used. And whatever the reject or unused material is coming out from the construction or the demolition things can be used, which can help us to reduce our CO2 footprint also. And there's a number of things can be also look into that, the chemical admixtures for cement and concrete. This can also reduce the overall consumption of the cement into our concrete, which means like a total footprint of the building or footprint of the concrete can be reduced. Nanomaterials and alternative materials also can be looked into the cement and concrete to reduce the consumption of the cement, which can help to reduce the CO2 emission or CO2 footprint. So contributing the focusing on the circular economy. This is the part we say that because a lot of drives are going on. I'm sure that everybody knows that. So how we can make it happen, which was not happening in the past. So this is the opportunity for all of us to look into that, reduce our footprint. Product and sustainable construction, cement, diverse portfolios. For example, in India, we have almost 16 standards. One is coming next few months time. So 16 standard, but 90% product is only for the three standards, like three applications, PPC, OPC, and PSC. These are three major components which cover the 90%. Look into that multi-component blended cement for the different application, because I can give an example. The cement which you need for the foundation, same quality and same thing may not be required for the plastering also. How can be application based and multi-component product can be developed for different applications and different usage into the whole different building. In one building, number of products can be done, which can also reduce the all CO2 footprint into the product side. So product development and product innovations can also be one of the area we can look. Concrete, as we discussed, that concrete is one of the area, because concrete is a final product. Cement is still, I believe personally, is the intermediate product. How this eco-friendly concrete can be built, how this other materials can be used to reduce the CO2, we call the kg CO2 per meter cube concrete can be reduced and make a sustainable construction. As I saw that Mr. Manu was talking about how significantly cement can be reduced, but similarly performance can be improved, durability, workability can be improved by using the different products. New products development, I think LC3 we already discussed, is one of the prime topic now industry is talking about. 3D printing can be one of the area. One of the things is geopolymer concrete, ultra lightweight concrete, and things can have quite significant product portfolio in the concrete also, which can help to sustain our construction as well as sustainability roadmap to fulfill that. So here we have to work on the product innovation, and product portfolio need to be enlarged. And I think again, coming back to we all know that few number of new standards are coming up. Maybe in the future we'll need number of application, number of product which can help to develop our sustainability in our construction. Innovation, I'll talk about this. These are new technologies, because as we discussed that whenever we limestone calcined, CO2 will evolve, germinate on that side. How can we do that? Yes, right now we do not have the immediate solution, but since research are going on. But meantime, what we can look into that? We can look at the carbon capturing, storage, and usage technologies. We can look the oxy fuel and oxygen enrichment, CO2 absorption, the concrete, that kind of things can be look into that to reduce our CO2 emission to the environment. And this will help us to achieve our net zero target into the commitment for sustainability. Process technologies now coming up, because now number of research are going on for the calcination technologies by the different different environments to reduce the CO2 or find the less energy in CO2 or combustion process or calcination process. And definitely this modeling of the process also one of the area which we are working on, that how to minimum energy input or minimum raw material requirement, how this digital technology or modeling can help us to reduce the consumption and avoid the waste in this whole process. What were the vertical safety margins, what call this one. Energy side, hydrogen is one of the area which is coming up. I'm sure that hydrogen will take one of the first lead into the Indian market very soon. Yes, there is a few challenges are there, but definitely that can be one of the immediately coming up. Solar energy as a usage of the electrical energy replacement is very much established in the Indian market. But now concentrated solar energy to use as a calcining energy is one of the area for the drying and calcination both can be the one of the application. Yes, technologies are under developed, pilot phase and coming up, where these things can be definitely help us to reduce our CO2 footprint. Material technology, this development LC3 is one of the biggest lever we see that currently, which can help us into our CO2 footprint reduction. And low clinker cement. This is the one of the area by using the different technologies of different materials. And red mud, LD slag, high MgO limestone, and copper slag. Things can also be help us to develop our product with the same durability and workability. Recycled concrete aggregates, carbonated and uncarbonated recycled concretes also can be the one of the area which you look into that. And product technology, look into the new carbon-based synthetic fuels, chemicals, admixtures, graphenes, new node tubes, kind of things can be look into that for developing our product performance, product efficiencies. So looking for this, I think we are exploring and partnering with a number of institutions as well as startups and research institutions to build the sustainability in our cement operations and cement business, which is very traditionally and conventionally look into that in the past. So now this opportunity for us to look into the innovatively our product to build for tomorrow. So thank you very much, someone from any questions, I'll be happy to answer the questions.
Sorry, thank you very much, Mr. Goel. We will be happy to take questions, but I would, since JK Lakshmi is also there, so there might be some questions which are common to both of you. So I would like to first take up. We would like to hear first from JK Lakshmi what is their ideas on sustainability and what they are doing, and then we will jointly take questions. And I am sure that there will be quite a lot of interesting questions. I can see a couple of them in the chat box also coming up. We will have a very interesting discussion.
Sure.
If you can stay back, sir, for a couple of minutes. Sure. Going forward, the last presentation, may I kindly invite Dr. S.K. Saxena from JK Lakshmi Cement. Doctor, we share a very personal rapport with Dr. Saxena from I think for the last five to 10 years. Dr. Saxena is working as the senior vice president, works at JK Lakshmi Cement. Previously, he was in Jhajjar. Now he has shifted to Sirohi, Rajasthan, and he has more than 34 years of experience in cement plant operation, quality control, and research and development. And under his leadership and Dr. Mukesh Kumar's leadership, we had first produced LC3 at the Jhajjar plant. Prior to joining JK Lakshmi Cement, he had worked in high-tech industries in Gujarat. He is also a member of various research committees, BIS, NCCBM, and has published more than 30 papers with 2 patents to his name in India. Over to you, sir. Pleasure to have you here.
Good afternoon. Thank you, Soman, and thanks for giving me the opportunity and invite me in this seminar, which is of high value, of course, in the present days of working. Almost all the development, all the initiatives taken by the cement industry has already been explained by, talked about by my friend, Mr. Raju Goyal, who is working with Ultratech Limited. And of course, the sustainability approach we have talked about, and the development of the LC3 and the current scenario of industry inching towards the net zero, of course, as far as the national imperative is there, and as per the COP26, what India has promised. First of all, I should extend my thanks and gratitude to Professor Karen, who has taken the initiative on LC3 and put a great effort in India also, just percolating the idea of LC3 since last 10 or 15 years. And My gratitude to Mr. Suman Methi also, who is taking great efforts, and of course the academia, IIT Delhi, IIT Chennai. They have done a wonderful job on development of LC3. We have Professor Getu has already talked about the LCA. Professor Manu Santanam has already talked about the field application of LC3, etc., which has strengthened the cement industry, of course, and given us the impetus for working on LC3 and working on LC3 in the future also. I belong to JK Lakshmi Cement Limited, which is a...
Sir, can you just so एक बार interrupt करो? Can you please put it in full screen mode?
Actually, Bharti is taking.
Acha, Bharti, can you please put it into full screen mode?
Yeah, Bharti?
Yes, sir.
Yeah.
Thank you. Thank you.
Yeah, this is perfect.
So this is one of the oldest organization having the history of 140 years, and it is an eminent and leading group in the country, and we are committed to the steady and of course the sustainable approach growth in the industry, and we always maintain the highest standards by adopting the latest technology, periodically upgradation of the production, quality control, etc. Next, please. Bharti, next slide, please. This is our JK organization, where we are in paper, we are in tire, we are in agriculture business, we are in banner, cleanerics, and of course in the Umang dairies. Next slide, please. So as we talked about, concrete is the second most consumed material after the water, and the industry consumes a lot of raw materials and energy and emits considerable amount of carbon dioxide, responsible for global warming. Already we have talked about the cement industry. As far as the CO2 emission, the contribution is around 7%. And at a time when the Indian government has promised drastic cuts in the industrial emission, and collaborative effort shows how the industry and the academia can use their synergy to find innovative solution to fight the climate change. And of course, the IITs and the TARA has taken a lead in that area. They have done a great job. They have created the awareness while having the collaboration and all. And of course, Mr. Mathi has done a good job as far as the mapping of the calcined clay is concerned in India, which is unfortunately not available in the IBM, etc., which needs to be addressed there. Next slide, please. We are talking about the net zero target for India, which has already been promised by our respected Prime Minister in COP26 summit at Glasgow. A net zero target of India by year 2070, installing non-fossil fuel electricity capacity of 500 gigawatt by 2030, and sourcing 50% of energy requirement from renewable by 2030, and reducing 1 billion tons of projected emission from now till 2030. This has already been talked about. In November 21, India has already reached an emission of reduction of 28% and has met the 40% target of non-fossil fuel-based installed power capacity as per commitment in COP21. The proactive steps also have been taken by the Indian cement industry, has contributed to achieve the goal of reduction in carbon dioxide, which has already been explained by my friend Mr. Raju Goyal. Now, there are certain levers which will be helping us in decarbonation of Indian cement industry, the substitution of clinker. Of course, we are producing, as already explained, the 63% already PPC is there, and 7 to 8% is PSC is there almost. The substitution of clinker, and what we are looking for also, as far as the reduction of clinker ratio in the different grades of cement. What we are talking about, like PPC, PSC, and the composite cement, of course. As far as the alternate fuel and the raw materials are concerned, cement industry is working very well on this. The fossil and conventional fuel is already being replaced, and in India, cement industry is leading, and we are thriving to achieve as much as possible the total substitution rate. TSR, which has some of the cement industry has already achieved up to 30% level. And the AFR is taking a leap as far as the replacement of the fossil fuel is concerned. Almost all industry are behind that, and quite a good progress is taking place in cement industry. The third lever is the waste heat recovery system. Almost now it has become the hygiene, and almost the whatever the new green fields are coming, that WHR has become a combo of that. Almost as Ultratech has taken up to 34% replacement in JK Lakshmi Cement also, we are around 33 to 34% of the renewable energy which we are using, and waste heat recovery almost we have installed in each and every plant, and almost 30 to 35% replacement of overall energy is by the waste heat recovery system. There are a lot many has been done as far as the improving in the energy efficiency is concerned. Lot many steps have been taken by the industry, and if you look into the figures of the specific heat consumption in cement industry, it is as low as compared to the world, and somehow we have reached up to the level of say 68 units per ton of cement. New technologies like renewable energy, which we have talked about, the novel cements, this is a new concept which is coming, where of course the as much as low clinker factor should be there. Carbon capturing, carbon sequestration, storage, utilization, these are some of the levers which will definitely be going to help us. First 4 levers have already been implemented by cement industry, and the impact has already been reflected in the reduction of CO2 emission factor from cement industry. However, to further reduce CO2 footprint of cement industry, we have to go for new low carbon cement, and LC3 one of them. This is recently on 3rd of May in 2022, we have entered in agreement with Tara, and one MOU has been signed by our respected President and Director, Shri Arun Shukla ji, on 3rd May 2022 at JK Lakshmi Cement Sirohi for achieving its carbon neutrality target by 2047, which we have committed through the production of limestone calcined clay cement LC3. The IIT and Tara and JK Lakshmi, we have a collaboration and jointly worked together on LC3 and carried out the full-scale plant-scale trial production of a new cement known as the limestone calcined clay. And with proud, I must say that Lakshmi Cement has become one of the first industry in India, rather in the world, where we have commercially produced the more than 500 tons of LC3 cement at our one of the entity in Haryana, which has been mentioned by Mr. Soman Methi, and that was a great story to relish, where the collaborated efforts have been done, and that is I am going to take it forward. IIT Delhi has been the leading, and of course the Tara, where we have planned this activity, and this is what I'm going to show you. Next slide, please. And of course, as we have talked about the raw material like the fly ash, slag, which is nowadays available, but as far as the commercial uses are concerned, and the cost of the material, which is day by day increasing, nearly, if I am correct, in industry, the fly ash landed cost which we are receiving for utilizing and making the blended cement, it has already crossed more than 1,000 rupees a ton. Calcined clay is the option, of course, for the future of cement manufacturing due to the increasing levels of the supplementary cementitious material like fly ash in the production of cement. But the availability is now becoming an issue now also, and because of low compared to the demand of cement, because normally we are shifting from OPC to PPC very fast. Calcined clays are the only other material that are potentially available in large quantity in India, which has already been mapped by Mr. Suman Methi, and the data already reflect that ample amount of quantity of calcined clay is available, which we are looking for the calcination, etc. And one more thing, beautifully he has mapped the deposits of clay in and around the integrated plant. That is also available. So by which we can see the ample quantity already is available in country. And the development of the LC3 specification is concerned, it is at the almost at the final stage of consolidation, or I would say the validation. It will be shortly published also. Next slide, please. This is the journey of manufacturing of LC3 at JK Lakshmi Cement, Jhajjar. Just it is a sequence of 4 years, I would say 4 years of rigorous work on that in a planned and systematic way in collaboration with Tara and IIT Delhi. And we could conclude the production in 2017. Next slide, please. So this is the approach we have adopted and the way we have forwarded as far as the production of the LC3 is concerned. The selection and the quality of raw material was the first foremost thing, where we have scouted number of reserves available in the western part of the country. Then we find that the calcination facility was also available there. First of all, we scouted the sites, then collected the raw material, get it tested for the suitability, etc. Then at the site of the calcined clay deposit, we did the calcination, maintained all the parameters. That was a difficult task, of course, because it was a conventional type of kiln where it was very, very difficult to maintain the required temperature, etc. But with our past experience of the kiln operations, etc., we could do it, we could manage it. And proper quality has been calcined, and characterization, etc., thoroughly has been done by in a collaborative approach, particularly using the facilities at IIT Delhi. Then we have shifted this clay, calcined clay, from that place to northern part of the country where our plant is there. And most importantly, the material limestone, which has been used for making LC3, it is purely the maize residue available at our integrated plant at Sirohi, Rajasthan. The ample quantity is available, which has been shifted to our grinding site, and then it was used to the tune of 15%. This is the view of the raw China clay maize in the western part, from where we have selected this material and used for the calcination. Next slide, please. So this is the chronology: raw clay excavation from maize, then sun drying was there, wet clay at maize to remove the moisture, etc., to the extent possible. Then it was transported from maize to the calcination site where the kiln was available. Then it was purely conventional feeding through the conventional elevator to the inlet of the kiln by the hopper and all. Then the calcination was taking place with the conventional method, like using the pet coke, etc. And after that, some of the rejection was there, but ultimately we could achieve the required quality of the clay with the certain percentage of kaolinite, and then it has been tested at IIT Delhi, validated, then it has been shifted. Next slide, please. This is the view of the this kiln, conventional kiln, and this belongs to Shriram Minerals Bhuj. Right. Next slide, please. These are some of the glimpses of that site where we have shifted the clay, then the view of the calcination, etc. The final product which has been arrived after the calcination process, then it has been packed in the bags and it has been shifted to the site of JK Lakshmi Cement. This is the plant of JK Lakshmi Cement split grinding unit having 1.5 million ton capacity per annum, where we have decided to execute this operation of commercial manufacturing of LC3, where we have 2 mills operations, and where we have used this calcined clay. Of course, the clinker was available because we are already producing cement there. And the composition which was used, 66% calcined clay, limestone 32%, and gypsum, it was an LC2. And LC3 clinker ratio was 50%, 30% was calcined clay, 15% was mice residue, and gypsum 5%. So there were some assumptions and some confusions as far as the grinding operation was concerned, but with our own experience, and we planned this activity and successfully commercially produced the 500 metric ton of LC3. And these are some of the test results which we achieved. The standard consistency or the water cement ratio, it was 31.25%. Blane was, of course, it was on the higher side, which was expected, to the tune of 665 meters square per kg. Initial setting time was around 25, then final setting time was 100. Loss on ignition, it was expected, as it was 7.44%. And these are the compressive strength parameters at the different stages, like 3 days, 7 days, 28 days. And you will observe that it is as good as, or I can say good quality rather than other blended cement, which we achieved with this addition of clay and mice residue, etc. The residue which we kept on 45 micron, which was around 19.8% and 2.8% on 90 micron. There was no expansion, etc. Yes, please. So this is the view of the site of calcining the clay, where we have done it at Bhuj. So the team of Tara, IIT, and JK Lakshmi Cement were there for at least 3 days continuously. These are some of the media reports, etc., which has been published, of course. And one of the most important, which I would like to inform or to tell, that this LC3 we tried also in manufacturing of autoclave aerated concrete blocks, which we have an entity of 500 meters cube per day in the same premises of JK Lakshmi Cement grinding unit at Jhajjar, and we are regularly producing autoclave aerated concrete blocks there. And there was a demand of autoclave aerated concrete blocks for making an administrative blocks of Swiss Embassy, where this has to be used, and we produce this AC blocks with the 100% replacement of OPC by LC3 in the same proportion, and we supplied around 145 meter cube. And this building has been built with the use of this exclusive use of this AC block, exclusively manufactured with the use of LC3, replacing ordinary Portland cement. Now, this is a green building which has been manufactured, and this is a photo which has been taken at the time of inauguration of that administrative building in Swiss Embassy. So this was all about the what I should say, the achievement of commercial LC3 production, first in India, by JK Lakshmi Cement Limited at our Jhajjar grinding unit. So thank you very much. Most of the points have already been covered by my friend, but still we are progressing very well as far as the net zero target is concerned. Industry is doing very well, and probably the hard work which has been done by Tara and IIT academia like IIT Delhi, IIT Chennai, and which has definitely supported the industry, cement industry, now this becomes our duty to create the awareness among the customers, because it will be a new generation cement, it will be a new variety of cement, of course, will be a blended cement in the category of the blended cement. And definitely we look forward for the immediate, as Professor Karen has already mentioned, now there is a need of scaling it up, and speed is required, definitely, because the way we have taken forward by the different steps, where definitely academia has very much helped industry by drafting the LC3 specification, etc., put it to the national agency like Bureau of Indian Standard. Not many discussions have taken place. All the concerns on this LC3 about the quality, about the application, it has been taken care, supported by the IITs, studies, etc., and which has given a very good impetus for finalization after the draft circulation and the public domain, received all the comments, and ultimately, since we are in the different committees of BIS, there was a lot of discussion on the product quality and the uses, the application, and how it will be sustained, and like the durability studies, etc. But it has all gone through well, because the product is well proven. Now this becomes our duty, industry duty, to take it forward, to create the awareness among the common users as a new cement, which will be helping us to taking towards the net zero or zero carbon emission. Thank you very much.
Thank you, Dr. Saxena. As usual, that is a fantastic presentation, and we always get to hear a lot about what is the initiatives of JK Lakshmi. So before we open the floor for question answers and then discussions, what I would like to point out to all of you, including all the attendees and the panelists, is that the outcome of this webinar will be a short white paper. We call it as a sustainability declaration, and we are going to make it and circulate to all of you so that you can provide your inputs. We plan to put it to the Prime Minister's office and to the ministry so that they can take care and help us in moving this forward. So that's the ultimate aim of this. Now, there are, if anybody, all the attendees, if you are listening, hearing, if you have any questions, then please raise your hand to the panels. There is already some questions that has been there, but there is a person, Akhilesh, he wants to ask some questions. Akhilesh Singh Yadav. If you can hear me, can you please unmute yourself and ask?
Sir, JK Lakshmi Cement is working very hard with the LC3 cement, and also under guidance of our plant head, working very well, always way forward for the LC3. Thank you for presenting, sir. Thank you, sir.
Thank you. One question is very interesting that has been in the box from Sonali, is that to all of you, to Raju ji and Saxena sir also, is that does the industry at present have any definite pathways envisaged for carbon capture, use and storage in India? Whoever wants to answer this.
I would request Dr. Raju Goyal ji.
Yes.
So, Somen, can you just repeat that, because I missed the question?
Does what is your definite timeline, or do you have any definite timeline for carbon capture and storage use in India in the cement?
As you know, that there is a very difficult, very good question, but difficult to answer that question, because as you know that the technology is maturing, technology is on the ground now, and as you know that some of the industry is doing the pilot right now. So I believe that it may not be happening the 1 or 2 years time, but next 3 to 4 years time, I think you will see that cement industry also start doing the piloting, and capturing is very much mature technology now, I will say that. Only point what is the coming back to the very difficult part of that. After capturing, what you should the utilization. That is still puzzle has not been solved by doing this carbon capturing. But number of technologies are coming up. Like for example, now carbon cube, which is the one technology which you see that the captured CO2 can be used into the sequestration of the concrete.
Concrete.
And number of products can be also developed by the using this carbon which is captured on that side. So capturing side, I will say that is going to be can be happen very quickly, but use of that captured carbon dioxide will be the one of the challenge which you are facing the industry. But I'm sure that the way the industry is working and the number of pilots are happening, Saxonergy knows that one. Startups are working very efficiently on that to find the solution how to use this captured carbon to make it another product which can be offset the economics of that.
Okay. Well, Manu is there, Professor Manu Santanam is there, Professor Ravindra Gettu is also there. If you want to have any questions, you are also please feel free to take part in this and ask. Taking this forward, we don't have much time, but I have four questions to put it on, and it is not only to both of you but to everybody. Number one was that, do you think that there will be an issue of fly ash in the coming future? Future means I'm talking about a decade, 10 years, 20 years, or 30 years. With the kind of emphasis of the government in moving towards renewable energy.
Yes, Somen, that is going to be there. Yes, we are still already we are seeing this scenario where we are not getting or not able to get the sufficient amount of fly ash which is required for cement grinding operations, particularly in the blended cement. And if you see, the consumption of fly ash to the tune of 35% has already been achieved most of the cement industry, and we are blending to the tune of 35%, which is maximum allowed by BIS, number one. Number two, it is also this composite cement is also getting momentum where there will be a blend of slag and fly ash will be there. Again, there will be a strong uses of fly ash. On the other hand, you will observe that what I told earlier also, that the cost of the fly ash is also increasing day by day, which is the area of concern for the cement industry. Why? Because since last 2 years, cement industry is already reeling under so much of pressure on account of the high increase of the fuel cost. That is why we were talking on fast replacement of fossil fuel by AFR, and industry is doing very well on the use of AFR and to the tune of extent possible. Again, there can be a issue of availability of AFR also, but still there are lot many AFR is available, and we are going through the technology, properly organizing the uses of AFR, which will help industry to take it forward. But definitely there will be going to be an issue of availability of fly ash, and that is why we need to fast scale up the use of this calcined clay and start the production of LC3, of course.
Thank you, sir. Thank you very much. Yes, sir.
Add one more point on that as per your concern on that SCM's availability in the future. So if I see that, I think India is just 10 to 15 years behind the Europe, because the situation of the Europe currently is no SCMs are available, because given that Saxonergy mentioned that the green energy initiatives, WHRS, all reducing the thermal power dependency, and hydrogen is coming up in the market very soon. So the fly ash availability definitely is going to be a challenge. And second, I think India has announced that they will double the steel capacity. It means slag will be coming up. But again, the location and the logistics and the availability in the pan India will be the one of the challenges they be there. So yes, you are right. There will be a challenge to the SCMs in the coming future.
One question which comes into your mind when you are talking about AFR when I compare it with European industries, cement industries, where in certain countries, the AFR usage has gone up to 70% even.
Even more than that. So many,
More
even
than
more than that. Yes.
Is about 80%, 90%.
Yes.
So what it is holding India? Why can't India go? We are only around 10%, I think so. What
No,
is
Indian average is 5%.
so? What is holding? Then next, generally, question comes: what is holding us back?
Saxena sir, you will take this question, then I will update on that.
Then you can very well reply on that because we are in the same boat.
So,
Yes.
Somisa, I think very well. I think this very good question. I think we all have to think about that. What is the reasons for that? When we compare to the Europe and other countries, where the 70 or 80%, 90%, or I can tell you the number of the claims with a 96% substitution already achieved sustainably year-on-year basis. So what is happening? The whole ecosystem. When I say the ecosystem, means like all the municipalities, we have the waste, the sorted of the waste, quality of the waste. This all has to be established there. Right now, what is happening? Cement industry is eager to use this material. But second part is that because economics, quality of the, forget about the economics also. I think Saxena will agree with me. The quality of the waste which is available is very, very poor. 60% moisture in that, 40% moisture in that. Huge contamination, huge foreign materials are there, which is not helping industry to use it because industry is happy to use it. So I think whole ecosystem towards the segregation of the waste, because I'm sure that so many you travel a lot in the Europe. Every house, in front of the house, you see the 4 boxes there, right? Different type of waste in the front. Since in India doesn't happen that. So segregation is one of the issue at the source of the origin of the waste. That is one of the area which I think Indians, because I'm happy to see that number of malls and number of location, public places, this dumps are there. At least 3 buckets I have seen number of cases. So segregation, quality of the waste when improved, Indian industry can also achieve the similar kind of things. So here we need a support from the policymakers, government or the municipalities and the local authorities, how to enhance and how to build this whole system and provide this material which can be used. Because as you know that we are the cement manufacturers. I'm talking about myself and Saxena sir. We have no much knowledge on that side, right? So number of players are coming up, which is developing this waste management and waste organization to set up segregation and things. And second side, they're also working on the supply side of this. So whole if value chain has been created, segregated, call it the AF, and I think cement plants are ready to use that one.
Yes, yes.
One more taking from the QR from before I move into the audiences. One, I'm very eager to put up that question. What the presentation that Manu made and presentation that Professor Gettu made, which was that the LCA analysis that Professor Gettu had presented. I think that is, I'm making a comment. Now you can say yes or no. It is a very important tool for ensuring sustainability of the cement, not only for the cement production, but of your whole plant unit. And if we can quantify those, do the measurement, quantify them, and then it is going to go into a very, very interesting database for the government to also to take care of in the future.
Yes, Somen, first of all, I would like to compliment Professor Gettu. The presentation which he has shown, it is fantastic. There's no doubt about it. The way he has presented right from mice to gate, every area of concern he has taken care, and that particularly as far as the emissions are concerned. And this is the right way. Definitely, every industry, particularly cement industry, they should go through that LCA analysis, then consolidate, collaborate the data, and then we can consolidate the data can be presented to the government. Then this is the LCA of cement industry and where we are. Because one point which he has categorically mentioned at the start, energy and energy combo which we are using and how much of CO2 emission is taking place up there. Normally in cement industry, you will see most of the plants have start using waste heat recovery by putting a lot many capex on that. because it is the energy which is, of course, the highly economical and, of course, renewable.
Professor Gettu, if you would like to comment on this, would need your views.
Well, first of all, I'd like to thank Dr. Saxena for the kind words and the encouragement. I think the industry has to come forward, like he has correctly said. More plants we see. We have done about 5 to 10 plants. That is nothing compared to all the plants in the country. So,
Agreed, sir.
So if we have more people coming forward, basically it is data. The cost is almost minimal to do this. It's basically just pulling out data, and that we can, suppose we have at least 10% of all the plants covered in the country, then we can go to the government and say, look, there is an advantage of heat recovery. There is an advantage of going for multi-stage processing in the plants. You have to make it compulsory, and we can really show the gains that we have for the country. A lot of plants are doing very good work using alternative fuels, alternative materials. See, so much of waste material is being used in our cement kilns. We should show this, we should showcase this properly and see what is the benefit we are giving to the country by using these alternative materials and recovering heat and so on. So I think we should follow what Dr. Saxena is saying, and I wish more plants will come forward so that we have a sizable database to project and go to the government also.
Thank you.
Dr. Getu, one more thing I would like to speak on that. Normally, we are from the industry, and earlier we were busy in our business. Now, why I am thanking you, you should not say the kind word because it is always there. Because the academic, like people like you, what you are supporting us, and now how the academics and the industry is coming close together, that makes a difference. That makes a difference.
Good.
Thank you, sir. Thank you.
Thank you, sir.
There are 2 hands that has been raised, so I will just allow them. Yeah, Kushumanchi Sai Sri, if you can speak, please put your question. Please unmute yourself and you can ask, and then we move on to Imran Khan.
Maybe she is not able to unmute. Does Bharti have to unmute Sai Sri?
Or else we move into Imran Khan.
Yeah, or they can put their comments on the chat or Q&A also.
Imran, if you can please unmute yourself and then speak, or Bharti, if you can unmute Imran and then allow him to speak.
Well, there was a question from Imran Khan on the Q&A. What is the coal quality role regarding sulfur content in manufacturing of LC3 cement?
I would put it to Manu to answer this.
I don't know if I'm well placed to answer that, but of course, with respect to coal, the sulfur that is already in the coal, I'm not very sure how it would be affecting the overall quality, because ultimately we need to also do an adjustment for the sulfate in the cement. And yeah, it depends on the form in which the sulfur is available. Maybe Saxena sir, you have some...
Yes.
Yeah,
Yes, you are correct. And it has no, not much effect as far as the calcination process is concerned.
correct.
I hate to close this discussion, but well, we are already 30 minutes. We have, but there are some. Let me quickly go to some very interesting questions that we have. Any project site in India where LC3 cement used in large proportion for construction?
No, not yet.
We don't have it. We don't have it yet.
Because unless the standard comes out, we'll not be able to produce the cement in large quantity.
I still have. Okay, so
Nikki Jackson.
Nikki, he's also.
Yeah, I've already answered that question, whether it was heat cured.
Fine. Yeah. So just we would like to be, but everybody I know is extremely busy. So you have taken out your time from your busy schedule in in giving us, in attending this and giving us the feedback. What we are going to do is, this video has been recorded in YouTube, so just some logistics arrangements. So we will put it in the website, and we have all of your emails, so we will share it with you. The presentations that everybody had made, we are going to compile it and then send it to, put it in our website, or have it, or send it to all of you, so that you have it. You all have our email IDs. You are free to discuss anything. We would like to take this forward. And what I told you is, me and my team, we are going to work on, along with IIT Madras and Professor Scrivner, we are going to prepare a white paper, which we call it as a sustainability declaration. And once we make it, we are going to run it through all of you, so that you can provide your feedback, because we need to submit it to the government, so that the cause of LC3 and the cause of sustainability can be accelerated. I would like to take this opportunity in thanking our esteemed panelist, Mr. Raju Goyal from Ultratech Cements, Dr. Mukesh Kumar from JK Lakshmi, Dr. SK Saxena for JK Lakshmi, and of course, nonetheless, that Manu, I don't think I need to thank him, because he is a part of the team from Manu and Professor.
Let me give this opportunity to thank Mr. Manu Santanam, who is always available to industry. And what I will again request to IIT, Professor Gitu, Professor Santanam, and you and your team, we need great support ahead in future also from the academics, just to strengthen ourselves. And the way of study you carry out has got some meaning for industry. So let me thank to all of you from my side. Thank you.
Thank you, sir, very, very much. Thank you very much.
Thank you. Thank you, sir.
Thank you to all of you.
Thanks.
Thank you, Raju ji.
Bye.
Thank you very much, sir. Thank you. It's a pleasure to talk.